Thank you. I'm Pablo Ampuero. I'm a member of the organizing committee of this NCNet webinars, and welcome back to our first virtual workshop of SZNet. We have the pleasure today to host Whitney Behr. But before I introduce Whitney, I'm going to say a few words about what SZNet is. So it is an international component of SZ4D. It is a coordination network of networks. We are working towards building an international community that studies subduction zone geohazards. And specifically, we would like to define the limits and possibilities of predicting geohazards. The main missions of SZNet are to compare observations of subduction zones around the globe with a common data set and understanding, to cooperate to consistently instrument critical subduction zones that can provide us with key and transferable insights, and to develop and nurture an international and diverse cadre of early career scientists that is equipped to make the necessary breakthroughs. We welcome your feedback. There's two links here that will also appear through the chat. On the left is for you to give us any suggestion on future workshop topics and potential speakers. And to the right, we have this anonymous demographic survey that you're also welcome to fill. And so let me introduce Professor Whitney Behr. She's currently a professor at ETH Zurich, professor of structural geology and tectonics. She's also the head of the Geological Institute at ETH Zurich. She was previously assistant professor at UT Austin. She graduated in 2011 from USC. And her research in structural geology and tectonics is a great example of the synergy between field observations, analytical and experimental methods, also modeling to constrain the mechanics of deformation and faulting, the rheology of the crust and the upper mantle. And for her research achievements, Whitney has received several honors, including in 2019, the Presidential Early Career Award in Science and Engineering. And she's a fellow of the Geological Society of America and has also received the Jason Morgan Early Career Award by AGU. So without further ado, we're looking forward to your talk, Whitney. The floor is yours.
Thanks so much, Pablo, and thanks to the conveners for the invitation. Let me get my slides set up here. One second. Okay, hopefully you can see that okay. Right, so thanks everyone for coming, and thanks to the organizers for the invitation today. My talk today is going to focus on constraints we can place on deformation mechanisms and rheology of the subduction interface in the deep slow slip and tremor source region, and I'll be trying to sort of compare and contrast observations from geophysical constraints on slow slip in modern subduction zones to features we see in the rock record, specifically exhumed rocks, and I'll be focusing a lot on rocks exposed on the beautiful cycladic island of Syros in Greece. And this work has been ongoing in my group for several years now and has involved a lot of wonderful students, postdocs, and collaborators, including those listed here. It's been funded for the last several years by an ERC starting grant I received in 2020, along with several internal sources at ETH Zurich. All right, so to start off, I know that the audience for the seminar is broad, and some of you may be very familiar with the topic of slow slip, but it might be new to some others of you. So I want to just give a quick overview of what slow slip and tremor actually are before I delve into some of the details. So this figure shows the types of transient deformation typically observed as a function of depth in subduction zones And at shallow depths, several regions record very low frequency earthquakes, and in some cases, shallow slow slip. Beneath that, we think of the megathrust as commonly locked and accumulating elastic strain. But when it does slip, it slips in what we think of as sort of normal megathrust earthquakes that release seismic energy in a matter of seconds. And then deep slow slip and tremor occurs down dip of the lock zone and involves geodetically detected slow slip that tends to occur over months, usually accompanied by seismically detected low frequency earthquakes or tectonic tremor that occur more frequently, sort of on a daily or weekly basis. And here we can look more closely at some of the characteristics of slow slip and tremor over time using this nice example from EarthScope for Cascadia. Here, the blue dots are geodetic measurements of plate boundary displacement along the subduction zone. And they show that overall, the plate motion rate is broadly continuous, and the average represented by the green line here is consistent with the rate of convergence across the subduction boundary. But then in detail, the plate motion is punctuated by these sort of accelerations in velocity represented by the red lines, and then these more rapid reversals in the plate motion that represent the slow slip events that are occurring over several days and recurring on a timescale of a few months. And then if you look at the blue sort of curve below, you can see that many of those plate boundary reversals or those slow slip events are also associated with spikes in tremor activity. So these are some of the typical behaviors that we see, or the linked phenomena of slow slip and tremor. And so these features were first discovered in Cascadia in the early 2000s, but they've since been detected at many plate boundaries worldwide and for a range of subduction zones with different thermal gradients. The orange ribbons on this map show the regions where slow slip and tremor have been detected. They're mostly concentrated along the Pacific Ring of Fire. And then the diagram on the right shows the thermal gradients for many of these subduction zones, which can be quite variable from cold to warm cases. The general depth of slow slip and tremor SST is from 25 to 55 kilometers in these regions. So in terms of sort of metamorphic facies, this spans the blue schist up to eclogite facies, and in some warmer subduction zones also includes amphibolite facies conditions. And ever since their discovery, people have been wondering what they mean and wondering what it is in terms of rock types, fluid flow conditions, temperature variations, deformation mechanisms that explain these different transient signals that occur as a function of depth on these plate boundary faults. So what I want to do today is summarize some of the constraints we have, firstly from geophysics on the deep slow slip and tremor source, focusing on the aspects that are potentially scalable or relevant to observations we can make from the geologic record. And then I'll switch to considering complementary information that the rocks can tell us and try to speculate on what some of the features that we see in the rocks might correspond to in the geophysical record. And again, I'll be showing examples from the cycladic blue schist unit on Syros Island, and I'll finish up toward the end, if there's time, by highlighting a couple of the many remaining open questions. Okay, so starting first with environment, this is an example from the Tokai district in central Japan from Kato and others. And the first thing to point out is just the spatial distribution of slow slip shown in the blue contours here versus tremor or low frequency earthquakes, which is shown as the green dots. Both are occurring down dip of the locked megathrust here, but the slow slip region from this particular event extended farther up dip and less distance along strike than the observed low frequency earthquakes. Then when we look at cross sections at features constrained by seismic velocities, on the bottom right, these are receiver functions, and they highlight the major velocity contrasts that are here, and the transitions from red to blue and back again define the upper plate moho, the lower plate moho, and the interface itself in the middle. The yellow stars represent the low frequency earthquakes, which appear to be located on the interface itself and near the mantle wedge corner. And then in terms of seismic velocities, we find that this part of the interface corresponds with a low velocity layer, as shown in the delta VS over VS figure in the upper right. In this case, those low velocities are associated with sort of subducting heterogeneity, in this case interpreted to be a subducting ridge segment. And then in the middle right, there's also this region along the interface of anomalously high VPVS ratios. And from experiment, these values of VPVS are only really compatible with both high fluid content and near lithostatic fluid pressures. So the interpretation from this paper was, as in the sketch, that there's some sort of downgoing plate heterogeneity associated with a subducted oceanic ridge that results in variations in fluid pressure shown in blue. And that's coupled with an upper plate cap rock shown in orange in the forearc that sort of seals fluids in and defines the slow slip zone. And then the low frequency earthquakes or tremor occur within that slow slip zone, but are concentrated just down dip where crustal eclogitization begin and where fluids start to kind of drain into the partially serpentinized mantle ledge. And an important thing to note is that the observations I just showed from Tokayo, this correlation between slow slip and tremor and a low velocity zone with anomalously high VPVS ratios is not unique to Japan, but has now been recognized in most other subduction zones that host slow slip and tremor. Here's a summary of the estimated VPVS ratios for a range of tremor hosting subduction zones. And you can see that compared to the low VPVS or low Poisson's ratio observed in the upper plate forearc crust of about 1.6 to 1.7, the slow slip and tremor regions characteristically show much higher VPVS ratios of up to about 2.8 or 3. And again, this is consistently interpreted to reflect both high fluid contents and high fluid pressures. So if we look now at some of the spatiotemporal characteristics of combined slow slip and tremor, this is a plot from Michel and others for Cascadia with time on the x-axis and latitude on the y. And it shows the along strike distribution of both LFEs, the black dots here, and slow slip events through time, which are the regions colored according to their slip rate. And there are a couple of key things to notice. Firstly, the LFEs define these sort of streaks or lineaments in the along strike direction that seem to light up repeatedly over time and recur quite rapidly on essentially a daily basis. And in many places, they're not accompanied by slow slip events. And then secondly, the slow slip events also define along strike streaks that seem to sort of repeat their location over time, but their recurrence intervals are much longer, on the order of months or multiple months, and they're typically always overlapping with or accompanied by prominent streaks of LFEs as well. So then here's a figure from Armbruster and others also for Cascadia events, but in this case is sort of zoomed in for the period 2003 to 2004 and looking in more detail. And here we see that the LFEs also show a sort of streaking type pattern, but in this case, it's in the down dip direction toward the northeast. And from 2003 to 2004, we can see that a lot of these same sort of streaks light up in the following year as if they're tracing persistent heterogeneities oriented down dip on the interface here. And then finally, we can zoom in at the scale of tens of kilometers, and we can see that individual low frequency earthquakes define small patches or families of 1 to 2 kilometers in length or width. And so there's clearly this hierarchy of spatial distributions that's defined at the minimum scale of a kilometer or so. But ultimately, these small features that we can resolve have to connect up to produce the large magnitude, up to magnitude 6 or 7, largely aseismic slow slip events. So then the third thing I want to highlight from the geological record is the spatial patterns of tremor migration, which have been interpreted as evidence that slow slip and tremor is accompanied by fairly rapid fluid or fluid pressure migration. So this is an example from Guerrero in Mexico, from Frank and others. And this figure is showing time on the x-axis again, and then each of the colored curves represent LFE counts for different down dip levels on the interface, with red being the deepest and blue being the shallowest. And this time series was recorded across a slow slip event that occurred from April to November in 2006. And what this shows is that at the start of the 2006 slow slip events, LFE counts rise all along the interface from shallow to deep. But then about halfway through that slow slip event, the LFE count starts to drop or decelerate substantially, first at the deeper levels of the interface and then progressively shallower along the interface until the end of the slow slip event. And this was interpreted as in this, this cartoon where at the start of the slow slip event, pore fluid pressures are high enough to generate failure from what's labeled here, the transient zone to the sweet spot. And this triggers a sort of acceleration in low frequency earthquakes represented by this signal. And it's interpreted as a sort of breaching of the upper plate seal and transient increases in permeability all across the interface from shallow to deep. But then as the slow slip event propagates, the fluid pressure is interpreted to start to drop first at the deep levels and then gradually migrate upward towards shallower levels. So that the idea that there's this migration of a sort of fluid pressure pulse upward from the sweet spot to the transient zone. And that migration has a sort of characteristic timescale of about 1 kilometer per day, which was interpreted if you assume that this represents some form of fluid or fluid pressure diffusion process. It was interpreted to represent or reflect permeabilities based on the diffusion coefficient of about 10 to the minus 12 meters squared, relatively high permeabilities. And in fact, several people have used this tremor migration rate patterns to estimate permeability. And here we've compiled sort of several from the literature. And they're all generally in the same range of this sort of 10 to the minus 12 meters squared, although the uncertainties are probably on the order of about 1 to 2 orders of magnitude, but still they cluster in this general area from this particular metric. So based on observations like those I just highlighted, the view from geophysics has developed into something like shown schematically here. There's this general concept of a heterogeneous fault plane where the locked part of the megathrust hosts these very large asperities that are tens to hundreds of kilometers in dimension, but then down dip these asperities are smaller and fewer on the order of kilometers, and they define these sort of patches or streaks both along strike and down dip. And then the low velocity and high VPBS ratios estimated from the seismological data suggest the presence of a very fluid rich and high fluid pressure environment. And the combined seismological and geodetic data indicate there's two distinct spatio-temporal event patterns. There's the low frequency earthquakes, which represent thousands of seismically detectable events that recur essentially daily. And then there's slow slip, which are these large aseismic sort of geodetically detected events that recur over several months. And additionally, the slow slip events seem to be associated with, in many cases, with tremor migration that's interpreted to reflect very high transient permeabilities of the order of 10 to the minus 12. So now I want to switch gears to discuss what corresponding types of information we can glean from studying the exhumed rock record. And so we can try to translate some of these observations to corresponding questions for geologists. I hope you all don't mind my ChatGPT, geophysicists, and geologist cartoons. But for example, when it comes to heterogeneities, we can ask what are the types and length scales of heterogeneities that we actually see in the rock record. When it comes to observations of transient events, such as low frequency earthquakes and slow slip, we can ask what types of transient deformation features we can see in exhumed rocks and what are the mechanisms that are associated with them. And then when it comes to evidence for rapid fluid migration, we can ask what the plumbing systems of subduction shear zones look like. And in some cases, we can try to quantify both the background and transient permeabilities for comparison to these larger scale estimates for modern subduction zones. So the way we get at this is by studying exhumed subduction complexes that have been brought to the surface through later tectonic processes. These are fairly globally distributed in orogenic regions. They're shown on this map as just these blue curves representing accretionary complexes in which blue schists and eclogites are preserved. And the processes by which these are assembled and then exhumed to the surface can be very complex and can vary from region to region. But in general, these subduction complexes all characteristically involve a process referred to as tectonic underplating, which is a form of accretion where fragments of the downgoing slab become sort of sliced off along megathrust shear zone segments and attached progressively to the upper plate. This is especially common in the deeper parts of accretionary margins. This is a nice example from numerical models that Jonas Rue and others conducted, and it shows how you can get these slices of oceanic crust and mantle sort of slivered off, and the active subduction interface consequent or progressively steps downward with time from sort of one rheologically weak shear zone material to another structurally deeper one, and you continue to accrete material structurally upward or downward with time. And many different rock types become juxtaposed in this environment, including sediments, mafic oceanic crust, sometimes slivers of partially serpentinized mantle. And oftentimes these sort of slivers are partially exhumed parallel to the subducting slab during ongoing subduction, and this contributes to their later preservation in orogenic belts. And so the particular subduction complex I'll be focusing on today is the spectacular cycladic blue schist unit. I'll use CBU in the southern Aegean. This is part of the active Aegean subduction zone, which has been accommodating convergence between the African and Aegean sea plate since the late Cretaceous. And the subducting slab was originally up here, but has progressively rolled back toward the south over time, and it's generated magmatism and induced back arc extension in its wake. And that extension has exhumed the previously subducted accretionary complex material, which is now nicely exposed on the Cycladic islands, which we'll be focusing on here. And so zooming in on the Cyclades, the CBU in this region records subduction and exhumation of both oceanic and continental fragments starting in the Eocene in this area. The subduction-related rocks, as I mentioned before, were exhumed initially along the top of the subducting slab under relatively cold conditions. And then later they were captured from the middle crust depths by detachment faults in the early to mid-Miocene. These are some of the faults shown here in white, the north and south and west cycladic detachment systems. And Syros Island, shown in the yellow box here, represents one of the structurally deepest and sort of the best preserved exposures of the CBU, preserving blue schist aquagite facies metamorphism in both oceanic and continental subducted slices. And I'll be showing examples from all over the island, but especially from regions that preserve features representative of sort of oceanic materials that are reasonable analogs for deformation you might see in modern Pacific style subduction zones. I'll especially be highlighting this area in northern Syros known as the Campos Melange Belt, which is a thrust sense shear zone that records north directed subduction and sort of suturing of a small ocean basin. It's one of the areas that very nicely preserves peak or near peak metamorphic conditions with relatively weak retrogressive overprinting. So it's a sort of ideal snapshot of the configuration and the deformation styles preserved in a deep interface shear zone. In terms of pressure temperature conditions, the rocks on Syros, they record conditions similar to warm subduction zones, such as Cascadia in Mexico. The peak metamorphism is estimated to be around 15 kilobars, and the early exhumation is constrained to about 12 to 14 kilobars. So both of these conditions overlap with the general depth of slow slip phenomena in modern warm subduction zones. Okay, so starting first with our question of the types and length scales of heterogeneity. So first, a quick note as to how structural geologists actually recognize rheological heterogeneity. Typically, we're looking for qualitative evidence of rheological contrasts, such as things like Boudin matrix relationships, where the strong materials form these sort of brittly dismembered blocks and the weak materials form a flowing matrix around them. We can also look at fold wavelengths, where the strong materials tend to define these large wavelengths, sort of buckle folds, and then weaker materials will often be folded much more tightly and kind of fill the interstices between those buckles. And when we apply these qualitative criteria in the field, we see this very common relationship where The most prominent heterogeneities nearly always involve juxtaposition of mafic oceanic crust and then sedimentary protoliths. And this produces heterogeneity for two reasons. Firstly, there's just a primary contrast in that mafic oceanic crust as an igneous rock is inherently stronger than oceanic sediments. And then there's a secondary effect that relates to fluid exchange across these contacts between sedimentary and mafic rocks that tends to produce much weaker, commonly phyllosilicate-rich metasomatic zones. This is shown just sort of schematically in this sketch of a potentially underplated fragment of oceanic crust that we might see is sort of brittly fractured and dismembered and boudinaged with metasedimentary cysts sort of floating around it. And then across the contact, we might expect a sort of metasomatic halo that is similarly weak as the sediments. So to show you some examples of these from cirrus, even though I think these relationships are preserved in many subduction complexes globally. But here's one of my favorite examples from Southeast cirrus that nicely shows this eclogite facies, sort of mafic pod embedded in a blue schist facies, metavolcanic and metasedimentary matrix. Here's another example from the compost belt in northern cirrus with this eclogite lenses embedded in marble and metasedimentary schists. And you can see how the metasedimentary sort of foliation just wraps around these features and encases the mafic lenses, and those mafic lenses are brittly dismembered and sort of stretched out by brittle processes. And then the second example of fluid-related metasomatism forming rheological heterogeneity along the boundary between sediments and mafic rocks is also very common and especially well-developed in the compost area of cirrus. Here's an example of a localized shear zone with metasedimentary schists on the right side and this sort of metasomatic shear zone in the greenish colors on the left. The matrix of this shear zone consists of chlorite, tremolite, and talc schist, and then embedded within it are these strong lenses of blue schist facies with relict igneous textured gabbro, and that's sort of dismembered and strung out as these semi-rounded blocks and boudins within the matrix. If we zoom in on some of the matrix material, we can see it forms a very high strain, essentially myelinitic foliation defined by chlorite, tremolite, and talc. And the high strain is what indicates it's weak compared to the sort of igneous textured blocks that are embedded within it. So then these qualitative data are entirely consistent, it turns out, with constraints from the lab. So here's a plot of viscosity as a function of temperature, and we've plotted it for temperatures of we would expect for the deep interface of 400 to 600. And you can see, consistent with observations from the field, that blue schist and eclogite, sort of mafic blue schist and eclogites, are expected to have 2 to 3 orders of magnitude higher viscosities for these conditions than metasediments or phyllosilicates. If we switch to looking at frictional properties, this relationship also still generally holds, with rocks like blue schists and gabbros and massive serpentinites showing relatively high static friction coefficients, and then things like mica, chlorite, and talc schist showing progressively lower friction coefficients down to especially weak for talc. So both the field and the lab support that these contrasts in mafic versus sedimentary rocks are primary sources of heterogeneity on the deep interface. But all of the examples I showed you are necessarily at sort of the outcrop scale, so sort of meter scale and below. And there's this general notion that geologists tend to get a little too excited about the outcrop to microscale and have difficulty scaling observations up to the kilometer plus scale that might be relevant to geophysical data. But the exposure on cirrus and actually in several other exhumed subduction complexes is good enough that upscaling to the kilometric scale is actually possible in this case. So our latest work, for example, has involved mapping some of these heterogeneities in that compost melange belt in the northern part of cirrus at very high resolution, and trying to follow structures and rock types along strike by about 4 to 5 kilometers, particularly with a focus on understanding the larger length scales of heterogeneity. And this is work in progress, but here's our preliminary map of the compost belt. All of the brownish and pinkish colors generally are the strong phases. represented by mafic oceanic crustal protoliths. And then the other colors shown on the right here represent metasediments and metasomatic products of sediment mafic rock interactions, so the weaker phases. And if we restore or slip on some of the late faults, we can sort of reconstruct the original subduction shear zone configuration with all of its inherent glorious heterogeneity that it would have preserved when it was at the conditions of slow slip and tremor. And then if we equate lab-derived physical properties to the rock types that we've mapped here, we can more directly investigate sort of along and across strike variations in physical properties at a kilometer and above length scales. And again, this is work in progress, but just to give a sense of what we're trying to achieve, I plotted some heat maps of this shear zone to try and illustrate the large scale heterogeneity in both viscosity and friction coefficient. And you can see that there's some significant kilometer scale sort of viscous and frictional heterogeneities or asperities, if you will, preserved here. And then several smaller variations in viscous and frictional properties expected in between them along this sort of central thinner part of the shear zone. So the take-home message is that heterogeneity we see at the outcrop scale is commonly mimicked at the kilometer scale, and there are indeed kilometer scale sort of asperities consisting of mafic fragments preserved in high strain shear zones, and these are preserved even at deep subduction conditions. And we think these may be sort of comparable to persistent tremor sources that are commonly seen in seismic data. So moving on then to the second question of the types of transient deformation features we can identify. So we have these large and small scale heterogeneities, but now we want to ask whether there's evidence that these heterogeneities actually did host some form of transient deformation that we can argue may have occurred over timescales faster than background aseismic creep. And this is quite tricky in subduction complexes because nearly all of them subducted to these PT conditions have some background deformation that is largely homogeneous and ductile viscous and probably occurred aseismically. For example, we see multiple generations of ductile folds in many places, as in the left photo here, or nearly homogeneously strained myelinitic rocks, as on the right photo here. But despite this pervasive background evidence for sort of aseismic viscous creep, it's also quite common to find evidence for coeval brittle or localized deformation. And we distinguish generally two forms, although they can often occur together. One is sort of cyclical brittle dilational and dilational shear slip that's common in or around the margins of some of these mafic lenses. The other is localized slip on phyllosilicate layers or shear bands, commonly also accommodated by veins that appear simultaneous or accompanied by veins that appear simultaneous or coeval. So to show some examples, coming back again to my favorite eclogite Boudin, this one is riddled with abundant veins, but also along its flank in the background, there's evidence of vein emplacement during progressive ductile rotation. So the idea is you have high angle emplacement of veins, but then you have subsequent ductile deformation that kind of rotates those veins progressively in a right lateral shear sense. And then you continue to do this through time such that you produce a vein array that looks like this. There's also evidence from this outcrop of simultaneous rather than alternating frictional viscous deformation. So this image shows brittle dilational shear fractures developed in the rigid eclogites that then sort of soul outward into the surrounding weaker matrix. And there it's deformed in a much more distributed viscous sense. And then we can also see these mutual cross-cutting relationships between slip on phyllosilicate-rich shear bands in the metasomatic zones and vein emplacement. Here's an example of metasomatized blue schist with many generations of veins that are sort of smeared out along phyllosilicate slip surfaces. Some of the veins are parallel or forming sort of C-type shear bands, and others are at high angles representing more S-type surfaces. We can see similar features if we come back to this example of the chlorite tremolite talc schist I showed earlier. So some of the veins in this foliation are transposed parallel to it, defining some of these not as weathered white streaks in here. And then some are at moderate angles, forming sort of shear bands or parallel to shear bands. And then some of the veins are even cross-cutting. And this is a telltale sign for structural geologists that vein emplacement occurred sort of simultaneous with gradual foliation development. We also commonly can see this type of behavior at the larger scale. Here's an example from a chlorite tremolite serpentinite schist in the compost belt. This shows blocks of massive serpentinite, as shown here, riddled with cross-cutting veins. That's sort of on the top and bottom of the photo. But then in the middle, we can see some through-going sort of slip surfaces or foliation planes developed. And there's also veins transposed within this foliation plane, as well as some that are cross-cutting at high angles or intermediate angles. And just a quick note to say that all of these cases that I've just shown you can be recognized as occurring under high pressure conditions because of the mineral assemblages that form within them. Things like high silica content phengite, high pressure chlorite, often other minerals such as glaucophane, garnet, or amphicite are preserved here. Additionally, at the microscale, it's also common to find evidence for crack seal textures that support the notion of sort of multiple incrementally opening events over time. And in general, it's well recognized that these vein features I highlighted are representative of high fluid pressures, and they're recognized actually in many subduction complexes around the world, not just here. But some of them, there's a couple of possible mechanical interpretations. Some of them may be most consistent with cyclical sort of increases and decreases in pore fluid pressure that leads to switches between viscous deformation and fracturing as the fluid pressure grows and allows brittle failure, and then it drops again and goes back to aseismic creep. Others may represent simultaneous sort of extensional fracturing and shear on weak phyllosilicate layers under relatively consistently high pore fluid pressures. Either of these are possible, and there are probably other explanations, but pretty much whenever you have dilational fracturing, it requires high fluid pressures. So we have these nice examples of brittle viscous deformation and slip on phyllosilicate shear bands that's coeval with vein emplacement. But again, we want to ask the question about upscaling. And so coming back to our restored map of compost, we've tried to do this upscaling in two ways. Firstly, we asked the question in the field as to how far we could trace some of these single sort of weak phyllosilicate rich high strain zones. And we mapped some of these zones in the field as far as we could, kind of walking along with our phone as a GPS to try to see how far they could extend. And this suggests that individual traceable sort of shear zones extend for about maybe a max of 1.5 kilometer distances in the along strike direction, but they don't really connect up to larger distances than that, at least in this exposure that we have here. The other way we've been trying to consider upscaling is to ask how far we can trace velocity weakening domains within the shear zone. So we compiled A minus B parameters from the literature shown here for our main rock types, with the numbers representing the normal stress value that the experiments were conducted at. And interestingly, the compilation indicates that the mafic materials such as blue schist and gabbro are the most velocity weakening rocks in this shear zone, especially at low effective normal stresses or high fluid pressures. If we look again at this as a heat map of A minus B, where the bright colors are velocity weakening and the dark colors are velocity strengthening, we can see this suggests variations in weakening versus strengthening length scales, again on the order of less than a kilometer or so. And you can imagine propagation of velocity weakening into strongly velocity strengthening areas along strike of the shear zone. So the take-home messages here are that we do indeed see transient deformation in the form of brittle fractures, as well as high-strain phyllosilicate shear bands, and these seem to occur cyclically with aseismic viscous creep. The maximum length scales of these features that we can trace in the field is 1 to 1.5 kilometers. Again, this seems compatible with the length scales we might expect for tremor events. But if we try to think of length scales approaching those of slow slip, we really struggle, because even though we have up to 4 kilometers or so of continuous along strike exposure here, we can't individually trace potential transient features all along that strike distance for more than 1 kilometer, for example. And I'll come back to this point briefly toward the end of the talk, because I think this is a kind of key issue of generating the length scales needed for slow slip. So to address our last question on fluid pathways and permeability. So the primary fluid conduits that we see on Ceros and actually in many other subduction complexes are some of the features I've actually already highlighted in some of the earlier discussion. So the plumbing systems in subduction zones tend to consist of 2 primary fluid conduits, the metasomatic fronts that develop typically parallel to the foliation, and then these cross-cutting sort of transient fractures or vein networks. And here's an outcrop that nicely illustrates both of these features, but these are found all over the island. And this is an image of a drone model of the outcrop that we focused on. It's about 100 meters in total length. And I'll just walk you through some of the different features that we see here and how we interpret them. So firstly, one of the main fabrics that stands out is the pervasive foliation defined by banding and transposed layering. We interpret this to represent bulk viscous deformation along the subduction interface shear zone, so formed under relatively slow background strain rates. But then superimposed on top of that foliation, we can see some features that relate to fluid flow. Firstly, we see some of these bright blue-green bands that are labeled with the blue arrows here. And we interpret up close, they look like this. They're dominantly a chlorite, so we refer to them as a chloratite, and they have these sort of diffusional or gradational boundaries with the surrounding green schist, which suggests they're metasomatic phyllosilicate-rich zones in origin. And then lastly, superimposed on both the foliation and the metasomatic bands, we can see an abundance of dilational and dilational shear faults, Boudin necks, and shear bands that have vein material precipitated within them. And I've highlighted a few of them in pink here, but there are many more that I didn't trace in this image. And so the way we interpret what we see in this outcrop is something like the sketch where the foliation and foliation parallel fluid conduits are transiently cross-cut by high angle fractures that represent a sort of breaching of that upper plate of the seal or the subduction shear zone seal. The veins eventually close and then start to become deformed by viscous creep in the interseismic period until fluid pressures build up again to produce a new set of transient fractures representing a new sort of sealing event. And this can continue over multiple million-year timescales. So these features seem to potentially resemble a sort of fault valving type mechanism similar to what several have interpreted for geophysical data, like that example I showed from Mexico earlier. So then we wanted to see if we could understand the permeabilities associated with these 2 forms of fluid conduits, the metasomatic zones parallel to the foliation and the cross-cutting transient fractures and vein systems. So first, if we consider the metasomatic chlorite layers, these by definition and by recognition of what they look like in the field represent diffusional or porous flow. And there's this nice set of experiments by Gansorn and others that specifically measured diffusional flow and permeabilities expected from chloratite. And they find that that process is quite slow, suggesting very low permeabilities of less than 10 to the 21 meters squared. So if anything, these metasomatic zones likely represent sort of permeability barriers at the timescales of slow slip. It's just much too slow to represent the slow slip transient breaching. In general, if we come back to our compost map and look at the distribution of permeability for all the rock types similar to, and generate these heat maps similar to what I showed before, we get a similar result that the background permeabilities can be quite variable, and that may be interesting in itself, the length scales of permeability change. but they're never higher than about 10 to the minus 19 meters squared. So they get nowhere near the 10 to the minus 12 to 13 that we might expect, or that we expect from things like tremor migration. So just showing that in another way, that these are all kind of the estimates from these sort of foliation, parallel or normal rocks at deep subduction conditions, and there are several orders of magnitude lower permeabilities than the tremor estimates. But if we turn now to look at the cross-cutting fracture systems, we've also been able to roughly quantify permeability in these using some key assumptions that I'll discuss in a moment. But in terms of methods, we first mapped the last generation of cross-cutting veins, sort of ignoring the ones that are transposed and assuming that maybe this represents sort of the latest or frozen-in version of the latest fracture network developed. Then we use this software package by David Healy called FracPack that allows us to make 2D permeability estimates from the mapped fracture pattern. And this software requires an estimate of the fracture aperture, which we assumed could be approximated by the width of crack seal increments measured in thin section in some of these dilational veins. Another assumption we had to make here was that the veins used in the permeability calculation represent an interconnected network that opened simultaneously or in very close succession. And this is a big assumption, but it is actually consistent with observations of mutual cross-cutting relationships between the veins and evidence for very high pore fluid pressures and low differential stress. There's sort of more detail and justification for some of these assumptions in our recent GRL paper, if you're interested in checking it out. Either way, these assumptions mean that our permeability estimates are sort of a maximum, especially this assumption of simultaneous vein emplacement. So this approach led to a permeability estimate of between 10 to the minus 14 to 10 to the minus 15 or so, depending on what we assume for the aperture. These represents sort of the upper and lower bounds of the apertures measured from crack seal textures. And there's slightly higher values expected across dip, but still relatively high values expected also along dip within a network oriented in this way. So then the take-home messages of this are firstly that these estimates start to get close to those estimated from diffusivity based on tremor migration. And given the uncertainty in those estimates, we could argue that ours are generally sort of compatible. And then secondly, this plot also demonstrates that the change in permeability from background to transient fracture controlled values ends up 6 orders of magnitude, which has important implications for models of sort of fluid-driven transient slip events. These are huge changes in permeability. And the last take home is just that this is only one sort of decameter scale measurement for the deep subduction interface, but we hope that others will try to sort of produce permeability measurements using similar methods and from similar large scale contexts so that we can try to see how representative this value of sort of 10 to the minus 14 actually are. So to summarize the potential view from the geological record, we envision the subduction megathrust transitions from a discrete fault in the locked region to this distributed sort of frictional viscous shear zone in the region of slow slip and tremor. We picture this also as an area of deep underplating where several fragments or slices of the downgoing slab sort of become stranded. This produces heterogeneous patches along the interface, residing both within and above the subduction shear zone. The primary source of rheological heterogeneity is these sort of brittle, commonly impermeable mafic lenses, as well as the phyllosilicate dominated surfaces around those mafic lenses that are especially well developed in sort of metasomatized fluid-rich zones. And then these paired mafic lenses and the associated weak shear zones can form sort of lineaments in both the along strike and down dip directions, and their length scales on the deep interface and the displacements recorded along transient features within them seem to scale reasonably well with the inferred moment of low frequency earthquakes. Additionally, these shear zones are highly impermeable over long timescales, but they do show evidence for sort of transient permeability changes associated with the development of fracture networks that can locally sort of change the permeability by many orders of magnitude. So there are several apparent agreements between what we see in the geology and the inferences from geophysical monitoring. Perhaps one exception is that the geologists seem to see relatively wide distributed shear zones at these depths as opposed to a discrete fault plane. But even considering either of these views of the interface, there's still some, well, many open questions. And I just want to take the last few minutes of my talk to highlight a couple of these. So the first one relates to how the kilometer scale heterogeneities that we see in the field and that seem to characterize the minimum scale of tremor sources, how they actually link up to produce the large spatial scale that defines slow slip, which is on the order of several tens to hundreds of kilometers. In other words, we have these weak shear zones with strong class or asperity-like features, as in these diagrams that are perhaps our tremor sources, but how do we occasionally connect those up such that they define subsurfaces of much greater area, but still remain slow and don't accelerate to become megathrust ruptures or at seismic velocities. And one option that Tara Scaria and I explored using numerical models was the possibility that transient discrete frictional slip events may nucleate in sort of rigid class within a frictional viscous shear zone setup as in the movie here. And what we found was that the viscosity of the matrix relative to the class and the percentage of the class would determine whether ruptures could propagate from where they nucleate in the class into the matrix. And if it's so, and if they do, what was the slip rate that they would achieve. And we found that if the matrix viscosity was too high, ruptures would accelerate through the shear zone to fast earthquake-like velocities, whereas if the matrix viscosity was too low, the ruptures would leave the class and then just immediately sort of quench or burn out in the matrix. And this effect is very similar to purely frictional models in which velocity strengthening materials sort of damp slip acceleration when the rupture propagates into the velocity strengthening region. In our case, the viscous matrix is the velocity strengthening source, and we're modeling it as sort of finite width shear zones as opposed to a single fault surface, so we're able to have multiple ruptures nucleating at once. And this particular model that's showing in the movie here shows the linking up of ruptures across the whole sort of model domain, connecting up multiple clasts, and yet the velocities of these ruptures remain relatively low, consistent with slow slip velocities. And through this suite of models, we sort of produced a regime diagram that shows the types of events we expect for different values of the matrix viscosity and then the classed densities. And this indicated that large slow slips should occur for viscosity values that are sort of intermediate. And what's meant by the threshold viscosity here is just the viscosity of the brittle ductile transition. And so this should be close to the brittle ductile transition of whatever material the matrix viscosity consists of. And this is the viscosity window where we expect slow slip, and that tends to sort of widen for class densities that are higher since it sets up higher stresses in the shear zone between the class. So there's a sort of threshold area at the brittle ductile transition where we expect these events based on this kind of model setup. And this is just one possible way that we could perhaps envision heterogeneities linking up spatially to produce these larger scale slow slip events. Another explanation that's been proposed by Adam Beal and Aki Faggring and Sue Ellis is this idea that in cases of high class densities, the class themselves may occasionally end up close enough to sort of interact and produce force chains that temporarily jam the subduction shear zone and then induce this sort of brittle stick slip behavior along the length of the shear zone that could potentially scale with slow slip. And these authors similarly looked at the class densities and matrix viscosities that are needed to sort of promote this jamming process. So these are just two possibilities for scaling up to slow slip length scales. And I'm personally biased toward explanations like these because I think they remain true to the rock record constraints that we have of distributed block and matrix type shear zones with mixed frictional and viscous deformation within them. But of course, these are just models, and lots of other types of models, including discrete fault planes, can generate these types of transient behaviors as well. So the models are really kind of non-unique in solving this question. Then one more key question relates to something I briefly mentioned earlier, which is how the transient deformation features we observe in the field should scale to LFEs or ETS events in time as opposed to spatially. And although we can never really assess the slip rate on individual transient structures in the rock record, besides to say that they formed faster than steady state creep, we can at least consider that one of the primary rate limiting components in these frictional viscous systems should be the rates of mineral growth in veins, because that closes the fracture system and allows the system to reset the pore fluid pressure. And so there's some potential for correlation between recurrence intervals of LFEs or slow slip events to vein precipitation and healing. And this has been looked at for minerals like quartz, both theoretically and experimentally, but from the literature, estimates of healing times seem to vary by several orders of magnitude, from timescales of hours to timescales of hundreds of years for temperatures representative of the deep interface. For example, this plot in the middle shows this suite of lab experiments done on microfractures in quartz, conducted by Brantley and others, and for temperature conditions of 400 to 500 degrees C. The x-axis is showing time, y-axis shows regression distance in microns, which is equivalent to sort of vein precipitation amount. And you can see that this plot shows vein precipitation rates of several microns on timescales of only a few hours for this temperature range. So this particular set of experiments would suggest that vein healing could potentially match the timescales of tremor recurrence intervals. On the right, though, I'm showing a plot from Fisher and others in which they used a theoretically derived kinetic model with two different sort of rate controlling mechanisms to infer sealing times, and plotted those up for typical subduction geothermal gradients. And even for a warm subduction zone like Cascadia, the maximum sealing times are on the order of 10 to 100 years, much too long to match either LFE or slow slip recurrence times, but perhaps more consistent, as the authors made in this paper, with regular megathrust earthquakes recurrence times. So the take home here is simply that our constraints on vein sealing and healing span a wide range that exceeds the range in recurrence intervals for all transient slip event types. So we need tighter constraints on these values in order to really evaluate the role of sort of fracture closure and timescale of veining and how it might contribute to control slow slip and tremor. There are a lot of other interesting open questions, but these are sort of two of the ones that I see as especially open to contributions, particularly from geology. So with that, I'll end here and leave my conclusions here for people to read, and I'd be very happy to take questions.
Thank you very much, Whitney, for this fantastic overview of all the information that we can gather from the rock record, especially from these exhumed fault zones, information about the deepest part of the seismogenic zone and beyond into the slow slip and tremor depths. I want to invite everyone to ask questions through our question and answer box or through the chat. I'm going to read the questions you write there. And let me start with the first. Well, let me start with one question I had. Actually, so there's a very interesting and important question about tremors, and more particularly about the low frequency earthquakes, LFEs. It is that they never grow to become large earthquakes, and their statistics seem to point to a characteristic length scale that's probably on the order of a few hundred meters or perhaps kilometer. And you showed us today that in the field you can see now this the ranges of heterogeneity is going up to the whole size of the outcrop, perhaps. And I was wondering what has been quantified about the statistics of the distributions of those heterogeneities in the field. And I'm thinking that some of the things I've seen in the literature maybe 10 years ago were descriptions in terms of power laws. And the power law doesn't have a characteristic length scale. So I wonder if now that you have a broader view of the field observations, you identify some characteristic length scales that could be candidates for this limiting scale of low frequency earthquakes.
Yeah, that's a good question. I mean, that's on our agenda to do in this compost area, for sure, is to actually calculate the statistics of the sort of mafic blocks. And that hasn't been done for this particular area. It has been done sort of at the outcrop scale in some melange belts. Saki Fagereng has done some nice work on that. I think that might be what you're thinking of that shows these power law distributions. I mean, so far, we do see that there's kind of a fractal distribution where we can recognize blocks on the meter scale. We can look also at the thin section and see little eclogite sort of lenses or pods even at that scale. And then we can see these giant sort of mafic lenses at the map scale. But I guess what we don't have is any scale larger than that. So we'll only have maybe 3 orders of magnitude to examine this over. And my guess is that we'll get a sort of fractal distribution, but I'm not sure we'll be able to see the limits, the upper limit especially.
Right, that would be interesting.
But the hope is that we can characterize. I think one of the nice things to be able to do would be to say that, or do this for many shear zones and see if the maximum length scale seems consistent, such that there's this idea that progressive deformation results in an ideal kind of distribution of these blocks at deep conditions, right? So that you start with much larger features, and then you sort of strain them enough that then they become dismembered to a certain length scale, right? And so that would be nice to be able to say, if we could look at this more globally, that there really is kind of characteristic pattern that you start big and you end up about this size at the end of the strain history.
Yes, that's an interesting point, which would be difficult to I guess reconcile with the observation of tremors and slow sleep also in the shallow part of the subduction zone, meaning that once you have broken them up into smaller pieces, you cannot their size cannot grow again, right? It's irreversible.
Yeah, that's true. It is common that some of these same features are dismembered on the shallow interface as well, and they form heterogeneities there too. That mafic blocks, are the strong phases on the shallow melanges as well. So there is a good point that sometimes, but there are cases where we seem to preserve them on the shallow part where they remain undeformed, and then they get dismembered when the temperature is high enough that they can start to engage in the deformation. But yeah, it's a good point that they are certainly observed as dismembered and Boudins in shallow interfaces as well.
So let me read let me read the questions here. The first one is a question about something that you didn't mention much during the talk. So it's a question by Anne Voigtlander. Thank you, Whitney, for this nice talk. I was wondering about the role of elastic strain energy stored in the fold zone. The strength, deformation, brittle or plastic response, and seismic activity, these are all related to the available energy provided to the system and potentially stored, which for convenience we turn into stress. So what would be the elastic strain budget part of a subduction zone? How much of it is released by deforming, fracturing, or rupturing? And what is the contribution to the in situ stress state and those on most of the geophysical properties?
That's a great question. I mean, the main answer is I don't know. I haven't been that quantitative with any of this yet. I mean, I guess I would picture a lot of the elastic strain as being accumulated in the megathrust locked zone, right? But then in addition to that, I think when you think of sort of straining these shear zones, especially in the case of like Adam Beal's models, where you actually have a bunch of clasts that are connected or rigid material that's connected, you can store some elastic strain before you finally overcome it and rupture. So it kind of depends on how we picture that. Even in the case of a shear zone where you don't have connected blocks, but you have rigid material in it, you can have different sort of stress magnitudes or yield strengths that those shear zones, at the large scale can attain or withstand before they actually plastically deform the blocks within them, if they do at all. So yeah, I think it's a good question, but I haven't looked at it super quantitatively. So it's a great question to ask those, is if we take these shear zones and we kind of deform them, how much is stored elastically in them compared to what we expect for the lock zone, for example.
And this probably you've seen in your models. This you've probably seen in your simulations with Taras, that maybe it depends a lot on the density of
yes, it definitely does. Yeah, absolutely. And we didn't actually quantify that, but it certainly does. That the time and the amount of strain that you need to accumulate before you can actually rupture the blocks is a finite length scale or time scale that depends on the distribution of the blocks in the matrix viscosity. But we didn't actually. Yeah, maybe I have a figure in there that would get at this question, but I can't think of it off the top of my head.
So here's another question by Baoning Wu. Thank you for the great talk, Whitney. And can you comment on cross comparison of the geological observations in these different environments? Like SSCs and LFE seem to be ubiquitous or to appear in many tectonic environments. Other than deep and brittle ductile transition at subduction zones. Maybe it's referring maybe to strike slip zones that also generate
Yeah,
tremors.
I think that's also a good question. So, I mean, the tremor producing zone on the San Andreas is interesting because it seems to coincide with a region where there's actually Franciscan subduction materials on one side. So like one way of interpreting it could be, you have kind of similar rocks, you have phyllosilicate rich zones, you have fluid rich material that was formerly subduction related. So that could be one way of interpreting that. Another could be that actually all faults have this signal, right? And this is just kind of the sound or the reflection of heterogeneity in fault zones. And the more we monitor them, like the San Andreas, which is really well monitored, the more we will start to observe them. And maybe they're enhanced in subduction zones because you're more likely with the presence of fluids to have a lot greater sort of rheological contrast, not only in the presence of fluids, but just the variety of materials that actually end up on these fault zones, where sometimes you can have fault zones that are granite on granite, for example, right? A strike slip fault that has similar sort of rheological properties and physical properties across the fault, whereas that's really rare in subduction contexts. So I don't know the answer. I think it'd be really interesting to start just, the more we start to monitor fault zones to see if more of them start to show these signals. Yeah.
So here's another question by Binhao Wang. Thank you, Whitney, for the great talk. Could you summarize what deformation mechanisms are observed in these rock records? Are there also healing mechanisms other than crack sealing that may match the recurrence time of slow earthquakes?
Yep, another good question. The deformation mechanisms are quite variable depending on the rock type, as you might imagine, but most common is a sort of pressure solution type process, which we expect for conditions of relatively low differential stress and then also a large role for fluids. And then in terms of other healing mechanisms, as opposed to crack sealing, I think of some sort of vein sealing as very dominant at these conditions because of how pervasive veins that cross-cut the foliation as well as end up transposed by it are at sort of all generations of strain. So on Cirrus, I only showed you some of the prograde features or what I think of as peak metamorphic features. But all the conditions, sort of the exhumation, the prograde part, the exhumation part is associated with this incredible amount of veining and fracture networks with veins sealing them. So that's the only mechanism that I've actually noticed, but maybe at the micro scale in some of these phyllosilicate regions, you might see some other form that doesn't involve sort of precipitation from a fluid. But I haven't actually looked for it. It's a good question. And I know, yeah.
So here's the last question in the chat from Diana Mindaleva. Thank you for the nice talk. I have a question about metamorphic halos in Greece. How about the width of these halos, and is it constant or variable in the field?
Yeah, that's a really good question, and we have been trying to document that, especially because it probably is relevant for this issue of whether the faults that define the slow slip region are narrow, discrete surfaces or maybe ductile shear zones. And they are really variable, and we actually have estimates of width from the compost area that I showed several times. I didn't show the actual width values, but we have been looking at the halos, and I would say they vary from half a meter to up to 3 meters, and not really more than that I can think of. So there does seem to be an upper limit to how much sort of metasomatism you can generate along these contacts. Yeah, it's a good question, and we hope that when we sort of publish this map, we'll have some estimates of the width of some of these features as well.
Okay, well, so with that, I don't see more questions popping up in the Q&A. So let me thank you again, Whitney, for this fantastic talk and for all these insights. And thanks everyone for coming to this webinar, and see you soon for the next webinar of this virtual SCNet workshop. Thank you.
Thank you so much, everyone. Bye.
Thank you.